Hi, and welcome to the second module of evolutionary ecology. In this module, we'll start looking at how ecology and evolution are intertwined, and our focus will be mostly on ecological interactions. But to really understand what we mean by ecological interactions, we need to know what the word ecology means, or what the field of ecology is. We've already defined this in class, and your book has a version. But for now, our working definition will be the study of interactions between members of a species and their environment, where by environment we mean both the biotic and abiotic components. As in the last module, one fundamental unit of ecology is the population. I know we've talked about populations in the first module quite a bit, but now we're going to take more of an ecological perspective to the concept. The book highlights 5 concepts, but for now, let's focus on 3 characteristics of a population that students often get confused about. The first of these is a population's range. The range of a population includes all of the places that its members may normally occur or live during their life cycle. You can think of this as a population's distribution, though that may be confusing to you later, so be careful. Populations may be wide-ranging populations like these great horned owls, or they may be very small-ranging populations that occur in very isolated locations. For example, the species shown in this slide only occur in one or a few places in the entire world. We call populations like this that only occur naturally in limited locations endemic. There are several endemic populations in Alabama, and even many in and around the city of Birmingham. For example, the vermilion darter is only found in the Turkey Creek watershed. It's a federally endangered species, and we've got it right here in Birmingham. Not very far away, the Bibb County Glades has 61 rare species of plants, 8 of which only occur in these glades and nowhere else in the world. That's pretty cool. Species often occur over separate ranges, and these subpopulations may be large or they may be small. For example, monarch butterflies are distributed as 2 separate populations in the United States, and they don't tend to breed with each other very often. That's why we call them distinct populations. But given that they can still interbreed occasionally, they are still members of the same species. Another way that populations may be distributed is in small, semi-isolated units or subpopulations, and these are part of larger metapopulations. In this figure, each of the shapes represents a separate patch of habitat that is either occupied or currently unoccupied by members of this particular species. When these patches are occupied, they constitute subpopulations. Patches are nested in a matrix of unsuitable habitat that keeps subpopulations from exchanging individuals very frequently. Because of this inhospitable matrix, each patch is mostly isolated, but there is some occasional immigration from one subpopulation to another. Ranges of species can change drastically over time, especially when humans move species around. When species are introduced into new ranges from their native habitat, they are known as exotic or non-native species. For example, kudzu was intentionally imported from Asia after the Dust Bowl years of the early 1900s to slow erosion, and now it is solidly established in the southeastern United States. Yeah, that worked out pretty well. Another important component of ecological populations are their dispersion, which is how individuals are arranged within a population. The dispersion of individuals can tell you a lot about the ecology of a species. For example, in this figure, in A, individuals all occur very closely together, and there are large gaps between groups. Why might they be dispersed in this way? The book has some pretty good suggestions. In panel B, individuals have fairly even or regular spacing between them. Why aren't these individuals clumped like in panel A? Again, look to the book for some suggestions. Finally, there is the intermediate condition of random dispersion. This is sort of a catch-all condition where the forces that would lead to uniform or clump dispersion aren't terribly influential. So, how do you think human populations are dispersed? Randomly, clumped, or in a uniform spacing? Think about this for our next class. The third characteristic of populations that I want to focus on here is that they change in size dramatically over time. All populations are either growing or getting smaller. They are pretty much never ever staying exactly the same, although sometimes we'll treat them like they do. Cockroaches are a good example of population growth, and this will really stick in your mind. If a population gets started with one pregnant female, it will grow pretty quickly. In fact, after just 3 generations, you might want to look away now. The result would be this. Yeah, that's pretty ugly, but it does demonstrate one form of population growth. They can grow exponentially, very, very quickly. However, populations can't grow exponentially forever because they'll eventually run out of resources or some other factor will limit their abundance. So, another way that populations can grow is logistically. They start out growing in what looks like an exponential fashion, but will start to level off. Have a look at the population here on Bird Island. The numbers of birds increases, then it stops growing at around 2,000 or so birds. This leveling off occurs when a population has reached its carrying capacity. What do you think limits the population size on these islands? It's probably some kind of resource limitation like food or nesting sites, but predators or disease might also play a role. Both of these two forms of population growth are shown mathematically and graphically here, and they show the same kinds of patterns you've manipulated in the semitext exercise for class. While these equations may look slightly different from the versions you've seen in the semitext or the book or in other videos, they are exactly the same. You should pause the video now to write them down. The first equation produces exponential growth, as with the cockroaches from earlier that grow quickly to a very large number of individuals. In it, the change in population size over time, dn dt, is a function of the maximum intrinsic growth rate and the current population size. In logistic growth, the equation is very similar with the exception of this term. The only new variable here is k, or the carrying capacity. This whole term represents the total amount of unused resources, and therefore is a way of including negative density dependence, from here on just density dependence, into the exponential growth equation. One thing to point out here is that at carrying capacity, every individual is just barely getting by. There's no surplus of resources, and things are pretty tight. Density dependence and density independence are terms that students frequently get confused. Both density-dependent and density-independent factors influence a population's size. However, density-independent factors have equal influence on populations of all sizes. In contrast, density-dependent factors have a stronger influence on larger populations and a weaker influence on smaller populations. Their role or their magnitude depends on how big the population size is. Density-dependent factors typically influence the birth rate, the death rate, or they may influence both simultaneously. At the point where the two lines cross, there is an equilibrium population size, which means that dn dt equals 0. Where does that happen in the logistic growth equation? Yes, at the carrying capacity. Birth rates could decline as population size increases because fertility rates drop or because females don't have enough resources to provision their offspring during gestation. Alternatively, death rates could also be density dependent if, for example, predators or diseases were more influential in larger populations. For example, with the bubonic plague. It was a big problem in cities where people were at high density, but not a big problem out in the countryside where people were at low density. Finally, both birth and death rates could be density dependent at the same time. In all three of these panels, in all three of these cases, wherever the birth and death rates are equal, then the population will be at carrying capacity. Note that the Crash Course Biology video does a really nice job of covering density dependence. Here's an example of density dependence in both birth and death rates. Here, the number of young per female, the birth rates, decrease, and the mortality rate, or the death rate, increases as the population gets larger. Where do you think the carrying capacity is? I'll let you think about that for class period. Returning to these two growth models, recall that exponential growth can't be maintained forever, since resources are never unlimited. Therefore, most populations are better described by logistic growth models that incorporate density dependence. Given this, let's put this in context of human population growth on Earth. If we start out with the recorded history of humans on Earth, we can start out over here. We have a very small population size. As the population changes over time, there are slight blips that go up. We start to grow much more quickly as we've domesticated plants and animals. We move into cities, and again, population growth increases more. There's a slight dip at the bubonic plague, but then the industrial and scientific revolutions hit, and we really know how to make people quickly. And the population grows in what looks like an exponential fashion. But recall from previous slides that no populations can continue to grow exponentially because they eventually start to run out of resources. Recall also that if you're at carrying capacity, times are tight. Everybody's got just enough resources to get by. So, what do you think will happen to human population growth on Earth? Will we keep growing exponentially? That's something that we'll leave for our in-class activity to discuss later. That's all I've got for now in this video. We'll build on this material with our class activity.